Welcome to another podcast. This episode, we're going to be taking a look at how to prove an if and only if statement. If and only if statements are primarily one of the most used statements in all of mathematics. All definitions are if and only if statements. So anytime you see a definition stated, you should know that that definition is this kind of statement. So it helps to understand the format of an if and only if statement, and I have a theorem here that's written as an if and only if statement. Even though it's not really stated that way, it is. So how do we write it as an if and only if statement? What does that statement look like? How do we go about proving it? That's what this episode is going to be about. So the best way to do this first is by diagramming kind of what's going on. The first part of this diagramming is to look at the phrase positive integer n. So this phrase is what we would call a general hypothesis. So it's a general sort of statement about, okay, what setting are we in? Then the next phrase that occurs is that integer n is evenly divisible by 3. This is what's called a predicate statement, so I'm going to give this the label A. And then the next statement is the other predicate statement, and it's the sum of the digits of n is divisible by 3. So I'm going to call that statement statement B. Looking at the way that we've sort of done this, the statement can be rewritten or rethought of logically as A, if and only if, and really I shouldn't use a double, that's for logical equivalence, but A, if and only if B. So this is called the biconditional. We will talk about truth tables for this later, but as a statement, the way to go about stating this is, or the way to go about proving this is to look at the forward direction first, meaning you want to prove if A, then B. And the way that you do that is you state the general hypotheses, and then you state, which is basically an assumption statement, you assume A is true, and then you have to construct the proof so that the concluding part of the proof is that you conclude that the statement B is true. So that's what we call the forward direction. The reverse direction is what you're trying to prove is that B also implies A. So once again, you restate any general hypotheses, and then you assume that B is true, and you conclude that A is true. So this is the basic format for proving an if and only if statement. All if and only if statements can be proved in the same way. It's just the particulars of the proof that'll differ from statement to statement. Now, just to get a sort of a handle on what this particular theorem is saying, the idea here is that suppose you were looking at, this is an example, suppose you were looking at the following number, and you wanted to know whether that positive integer is divisible by 3. So the question we're asking is, does 3 divide this integer? What the theorem is suggesting is that it will divide the integer if the sum of its digits is divisible by 3. So the sum of the digits here is equal to 21, and because 3 divides 21, then everything checks out. 3 will then divide this number, assuming that the theorem's true. We've yet to actually prove anything here, so we can't take this at face value. So in order to prove this, and one of the reasons I looked at the example is the example gives us an idea for how to go about the proof. So here's our first attempt sort of at a proof for this, and we'll talk about some of the parts of it as we go through. So I want to suppose n is a positive integer and I want to suppose that 3 divides n. So that is the first two parts. I stated the general hypothesis that n is a positive integer, and I'm assuming that the A statement is true, which means that n is divisible by 3, or 3 divides n. So suppose n is a positive integer and 3 divides n, and then let d0, d1, up through dk be the digits of n. Now, the digits are these things right here. So if I look back at my example, d0 would be 1, d1 would be 6, d2 would be 4, d3 would be 0, and so on. So this would be d4, d5, d6. So it's a 7-digit number, so k refers to the number of digits minus 1, or we could start it at d1 if we wanted to, but typically we would start it at d0. Then what we have is, based off this, we know we can express n using base 10 in this way. So this is just base 10 notation. This is how you create a number. You take its digits and multiply it by power of 10, depending on where it is for its place. And now I also want to let s be defined as the sum of the digits. We must show that 3 divides s. So that's the forward direction. That's what we have to conclude, is we have to conclude that n is divisible by 3. The sum of the digits of n, which is s, the sum of the digits of n is divisible by 3. So we must show that 3 divides s. All right, in order to do this, I want us to take a look at n minus s. So if I take n minus s, then this is just writing down what each thing is at this point. It's this, and what you notice is that I can pull pieces away from n via s, meaning that if I actually do the subtraction here, what you end up with is d1 times 9, because d0 minus d0, the first digit cancels. Then I have 10 d1s here minus a d1 here. So I've got 9 there, and then d2, I'd have 99 of those, all the way up until I have several 9s in front of dk. So this is, I've got 10 to the k dk's, and I'm subtracting 1, so there would end up being k. There's k of these. There'd be k9s in front of dk. And so what we observe at this point is that 3 divides n minus s, because 3 divides each one of these. You can see that 3 divides each of these pieces. So in particular, what we have is that n is equal to n minus s plus s, and since 3 divides n and 3 divides n minus s, then 3 must also divide s. Because if the left-hand side is divisible by 3, this piece is divisible by 3, then s must also be divisible by 3. And so that is the forward direction. And oftentimes in proofs what we'll do is we'll say, okay, this is the forward direction of the proof. Now, if we want to go in the reverse direction of the proof, there's really not much to be done here. The reverse direction is kind of easy. So I'll just say, conversely, suppose that 3 divides s. All right, so that's my assume b is true, so assume that the sum of the digits is divisible by 3. So suppose 3 divides s. Then I know that I can write n as n minus s plus s based off what we did previously. And so if 3 divides s, since we know 3 divides n minus s, then 3 must also divide n. And so we are done. Sometimes I'll put this little box at the end to mean that we're done. But the idea here is we have to prove it in both directions. Because we were able to prove it in both directions, what we know is that this is an if and only if statement. Positive integer n is evenly divisible by 3 if, so this if right here is really if and only if the sum of the digits of n is divisible by 3. It's a handy tool, by the way, to know this theorem. There are several divisibility theorems that we'll talk about over the course of the semester, but this is a really good one, knowing that the sum of the digits of a number divisible by 3 if and only if the number is divisible by 3. All right, thank you for watching.